the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to linear algebra students who are just going through matrix equations. You should have already learned all about systems of linear equations, row echelon form, and row reduction methods. You should know all about vector equations at this point, not vector spaces, but vector equations. And you should know quite a bit about matrix equations, but now we get to what is probably one of the most important theorems in the first half of the course, if not the entire course. This theorem gets larger as we move forward, so I'm just letting you know this theorem is not finished. I've mentioned it in previous videos that the author of the text that I use, he numbers his theorems if they're very important. This theorem is so important that it should be not just bold and italics, but maybe like 5 sizes larger. It is a massively important theorem. So let's dive into it. That's the only purpose of this specific video, is to talk about this theorem. This theorem is basically like an equivalence theorem. It's going to say that a bunch of statements are saying the same exact thing. So the following statements are logically equivalent given a constant coefficient matrix, which is an m by n matrix. And then I even clarify it by telling you what I mean by logically equivalent. It means that these statements are either all simultaneously true or they are all simultaneously false. In other words, if statement 3 was false, they are all false. If statement 4 was true, then they are all true. It essentially gives you options when you're working in linear algebra to try to prove something. You don't have to prove something only through one method. You have options now. So let's talk about each of these. They're all logically equivalent. So for each vector b in Rm, and I had mentioned in the previous video that b, the vector b, you can think of as being in the range of the product of the matrix A and the vector x. So this is kind of like a function in a way. It's not really, but let's just pretend it is. And b would be in its range. So anyhow, if it is true, and I'm going to state this entire theorem as if the statements were true, and then I'll go back through and state them as if they're false, okay? So if it's true that for each vector b in Rm, ax equals b has a solution, and that means no matter what value of b I throw on the right-hand side of that matrix equation, I should be able to solve it. Well, that's the same as saying that for each vector b in Rm, so kind of the same setup, b must be a linear combination of the columns of A. So those two statements, the first two statements, are exactly the same. If somebody told you, hey, for every b in Rm, that vector b is a linear combination of the column vectors of the matrix A, then you could say, oh, well then, for any b in Rm, ax equals b must therefore have a solution. But if either of those two statements are true, the following statement is also true. The columns of A span Rm. That is, the columns of A build the entire dimension Rm. So you could take, that's essentially saying you could take any vector in Rm and create it using the columns, a linear combination of the columns of A. Very, very similar to the statement number 2, actually. And finally, the last one, which is going to be incredibly important in this course, A, which is the coefficient matrix, has a pivot in every row. So if I told you that I had a matrix, a coefficient matrix, A, and it had a pivot in every row, that's equivalent to saying, hey, I'm going to multiply that matrix A by X to become some vector B, and no matter what that vector B is, I'm going to guarantee it has a solution. Oh, and by the way, B is a linear combination of the columns of A. Oh, by the way, A spans Rm. All of those are the same exact statement. Now let me say it backwards now. Remember, those statements are either all true or all false. So let's talk about the falsehood statements. When you do a falsehood statement or a negation of a statement, you generally say like, okay, what's the opposite of saying for every single B in Rm something is true? The opposite of that is saying there exists a B in Rm such that the following statement is not true. So I will write actually in red off to the right hand side the opposite statement. So that red ink right there says the following. If you've never done symbolic logic, that backwards capital E right there means there exists. So there exists some vector B in Rm such that the matrix equation Ax equals B does not have a solution. That's the opposite of this first statement. So if that first statement fails, basically that means this red ink is true. Okay, so we're now dealing with, well, what if one of these fails? If one of these statements here fails, they will all fail. So what's the all fail situation? What's all the language we need for all of them failing? Well, the first one, the opposite is, there exists a B such that Ax equals B does not have a solution. The second one says, there exists a B in Rm such that B is not a linear combination of the columns of A. It doesn't mean that every single B is not a linear combination of the columns of A. There just has to exist one that breaks the rule. The opposite of the third condition, the columns of A span Rm, is that the columns of A don't span Rm. And I also numbered these 1 star, 2 star, 3 star to say these are the opposite statements, the failure statements, if you will. And finally, the failure of the fourth statement. The fourth statement is that A, which is a coefficient matrix, has a pivot in every row. Well, the opposite of that is that it doesn't have a pivot in every row. And probably, now that I'm about to write this down, probably a better way to say it is A has at least one row that does not contain a pivot. So, in summary, very quickly, either all these yellow highlighted statements are true or they're false. If they're false, that means all these red highlighted statements take effect. It's probably easier just to remember the yellow highlighted statements and to be able to on the fly negate them, but I'm just showing you the negations of them here. This theorem is so powerful. I know I've already said it, but it's incredibly, incredibly powerful. Now I'm going to read through the notes very quickly and then we'll go through and prove a few of these. You need to understand why Theorem 4 is true. This may take some time and effort. Example 3 in the text, which was actually similar to the previous example in this lecture, which I'll show you right now. This example right here, which is in a previous video, it basically says if I have an arbitrary vector B, that Ax equals B does not always have a solution. Remember, B has to be in the span of the columns of the matrix A. And if the columns of the matrix A don't span all of your space, Rm, then you could accidentally choose a right-hand side vector for which this equation would have no solution. If you need a review of that, it is the video right before this in the playlist. But anyhow, that example should help along with the proof. Theorem 4D, this A, the coefficient matrix has a pivot in every row, can be restated as the reduced echelon form of A has no zero rows, which I think is a great way of thinking about it. That's such a good, understandable way of grasping the fourth part of this theorem, 4D. I called it D, but it's 4.4. It's this guy right here. All right, let's see what the second note says. The phrase logically equivalent is explained in the statement of Theorem 4. This phrase is used with several statements in the same way that if and only if is used between two other statements, right? So this is true if and only if that is true. I wrote here A, B, C, and D, but really here I wrote them as 1, 2, 3, 4. So let's just substitute that in. So saying that the statements 1, 2, 3, and 4 are logically equivalent means the same thing as saying that 1 is true if and only if 2 is true, 2 is true if and only if 3 is true, and 3 is true if and only if 4 is true, and 4 is true if and only if 1 is true, and so on and so forth. They go all around. They basically, all of them are true if and only if each other is true. To do this, I'm actually going to go ahead, I'm going to remove my ink here. That way I can actually see what I'm looking at To prove this theorem, I'm going to start with the first three, and I'm just going to do an if and only if chain, because you can do that with the first three. The last one you can't. You have to do a little extra work for the last one, but the first three actually are logically equivalent. So let's go ahead and try this out. We'll start with a statement: for any vector I grab from Rm, the equation, the matrix equation that is, ax equals b, has a solution. Well, that is true if and only if, actually, the vector equation x sub 1 a sub 1 plus x sub 2 a sub 2 plus so on and so forth to x sub n a sub n equals b also has a solution. And if you're keeping track of why that's true, that comes from a theorem that was introduced in this section of material, specifically Theorem 3. The solution to a matrix equation is the same as the solution to its related vector equation. And by the way, I'm assuming here that A1, A2 through AN are the columns of our matrix A. But if you want me to cite it, I will cite by Theorem 3, even though in your text it might not be called that. It is in mine, so I will go ahead and use that. But this equation has a solution if and only if B is a linear combination of those vectors A1 through AN. And by the way, that linear combination of those vectors, A1 through AN, is a linear combination of the columns of the matrix A. Those are the columns of matrix A. I'll actually just point an arrow at this. Kind of a sloppy proof to do it this way, but I'm going to do that. Well, great. We got that far. So we have proven so far that 1 is true if and only if 2 is true. That's what this means. 1 is true if and only if this sideline statement is true, which is true if and only if 2 is true. So through a chain of if and only ifs, we've arrived at 1 is equivalent to 2. But this statement 2 is true if and only if B is in the span of those vectors. And since we've made this statement for any B in Rm, that means that the span of those vectors has to at least be Rm. And that's at the very least. By the way, I'm not saying that the span of those vectors, the column vectors, I'm not saying that the span of those column vectors is Rm. I'm saying it's at least Rm. There is a subtle difference there. But if you look at the theorem that we have up above, the columns of A span Rm. They will generate all of Rm is basically what that means. And so we have that same statement here. The columns of A, which is basically what this is, not basically exactly what this is, spans Rm. So we have actually proven through if and only ifs that 1 is true if and only if 2 is true, if and only if 3 is true. So these three statements are now logically equivalent. There's no way around it. They're locked in. They're either all true or all false. They're think of them as switches. If you switch one on, they all switch on. If you switch one off, they all switch off. To prove the equivalence of the fourth statement to the other three, it suffices to just link the fourth statement to any one of these previous statements. So what I'm going to do is link it to the very first statement. I'm going to use the first statement to build an argument, mainly because working with a matrix equation, ax equals b, is a little bit easier than talking about linear combinations for right now. So let's go ahead and link statement 4 to statement 1 somehow. And the way we're going to do this is we are going to build an augmented matrix with the coefficient matrix A and the augmentation vector B. Now, we know that we can always get an augmented system or even a coefficient matrix into echelon form via row operations. We also know that the underlying solution, or the solution to the underlying linear system that is associated with ax equals b, is not going to change when we do elementary row operations. So, using elementary row operations, we are going to go ahead and say this can be reduced to the echelon form. All right, I did a lot of handwriting there actually, so let me go ahead and just read this out loud. So we can use row operations to reduce that augmented matrix down to a different augmented matrix. Obviously, row operations are going to change things, right? But remember, when you apply row operations, as long as they're legal row operations, you're not going to change the solution to the underlying linear system. So the solution to the systems related to those two augmented matrices will not be different. They'll be exactly the same. And we can go ahead and do that row reduction until we reach an echelon form. So U is going to be an echelon form of A. So we have basically traded out our original augmented linear system through elementary row operations for a new augmented matrix. Now we're going to start into the proof that 4 and 1 are equivalent statements. Once you do those two things, you've linked everything up. It's all of a sudden, it completes the circle, right? There's an if and only if between 1 and 2. So they're either both true or both false. There's an if and only if between 2 and 3. So they're either both true or both false. So therefore, 3 and 1 are either both true or both false. And now we're going to build an if and only if between 1 and 4. And once you have that link, 4 is true if and only if 1 is true, then since 1 is true if and only if 2 is true, then 2 is true if and only if 4, 3 is true if only if 4, and you then link everything up. All right, so let's assume that the coefficient matrix, our original coefficient matrix, has a pivot in every row. Well, if that's true, remember, U is just an echelon form of A, but the pivots don't change. So U has a pivot in each row as well. But if U has a pivot in each row, so row 1, 2, 3, all the way down to row whatever, it doesn't really matter, has a pivot in this coefficient matrix here, that means there's no room for a pivot in the augmentation column. That is, there's not a pivot in the rightmost column. And again, if you're using the text that I use, or if you're following through with all the theorems we've written down so far, by Theorem 2, the existence and uniqueness theorem of solutions to linear systems, if the rightmost column of the augmented matrix is not a pivot column, then the corresponding linear system must be consistent. Now remember, that means the system corresponding to U augmented with C. However, row operations do not change solutions to linear systems. So the solution to the linear system associated with this augmented matrix is the same as the solution to the linear system represented by that augmented matrix, A augmented with B. And because the solution to the linear system associated with U augmented with C exists, because the system is consistent, then the solution to the linear system associated with the augmented matrix AB must also exist. Note, I didn't tell you where I grabbed B from. In other words, I didn't give you a specific B. I just said, suppose that we have a B from, actually really from RM. So suppose we grabbed a B from RM, just a random B from RM. So therefore AX equals B for any B in RM. And that upside down capital A is, again, a symbolic logic statement. It means for every, or for each, or for all. They mean the same thing. So we have proven, if part 4 is true, that we have a pivot in each row, then part 1 is true. AX equals B has a solution for any value of B in RM. So great, we've proven 4 implies 1. Let's go ahead and prove that 1 implies 4. Now, to prove 1 implies 4, so that's me saying I've proved 4 implies 1, we now want to prove that 1 implies 4. And we're going to do this by contraposition. We're going to say, well, what if 4 is not true? Let's use that to prove that 1 cannot be true. That's contraposition right there. So we're going to do a proof by contraposition for that last piece. So instead of assuming that AX equals B has a solution for every B and proving therefore that A has a pivot in each row, let's start by assuming A doesn't have a pivot in each row and show that therefore AX equal B does not have a solution. Well, if A has a row without a pivot and we row reduce to this form right here, the echelon form U augmented with C, then because U is an echelon form, remember in echelon forms, all 0 rows end up at the bottom. And since we have a row without a pivot, that row must have all zeros. Now remember what we're trying to do here. We're trying to prove that if 4 is not true, that is, A has a row without a pivot, then 1 is not true. And remember, let's take a look at 1 here. 1 is that for each B in Rm, A equals B has a solution. Now we're going to say we want there to exist some value, some vector in Rm where Ax equals that vector does not have a solution. Well, one very easy vector to choose. We're going to let C, again, we're kind of working with this augmented matrix right here. We're going to let C be any vector in Rm where the very final entry is non-zero. Now remember, U is the echelon form of A, and we're pretending as though right now that A does not have a pivot in every single row. There's at least one row without a pivot. So therefore, the echelon form of A will have a 0 row at the bottom of it. So that final row at the bottom of the augmented matrix is going to look like this. A bunch of zeros in that final row, and then a non-zero number, which tells us that the augmented matrix will have a pivot in the rightmost column. Again, hearkening back to Theorem 2, the existence and uniqueness of solutions to linear systems theorem. If the rightmost column of the augmented matrix is a pivot column, the corresponding linear system is inconsistent. But remember, if the linear system corresponding to this augmented matrix is inconsistent, we can just do the same row operations to build back to A augmented with B, and because they're row equivalent matrices, their underlying systems are also equivalent. In other words, they have the same solutions, or if they don't have solutions, they both don't have solutions. And I write it shorthand here, hence the linear system is inconsistent, but really I mean the linear system associated with U, the echelon form of A, augmented with C. Remember, you can do the inverse of row operations, so you undo all the row operations that got you to U augmented with C, and you'll get back to A augmented with B. And remember, row operations don't change solutions, so the fact that the linear system associated with this guy doesn't have a solution means the linear system associated with AX equals B also does not have a solution. And so we have found one vector at least, actually there's an infinite number of them, but let's just say we found one. We found one vector in Rm such that Ax equals that vector does not have a solution. And so we have proven that if 4 is not working, in other words, we don't have a pivot in that bottom row, then 1 is not working. In other words, there is at least one vector in Rm such that Ax equals that vector does not have a solution. So that is the proof actually of the entire Theorem 4. Actually, it's kind of a big proof there, but one of the most important theorems that you're going to have this early on in a linear algebra course. I highly recommend you spend a lot of time playing with problems in the homework that your instructor assigns that allows you to flex your muscles with these. These properties are super powerful, and once you get used to them, they're really nice and easy to use, but you do have to get really used to them. All right, I know this is a longer video. I apologize about that, but I hope you have a great day, and I'll see you in another video. Have a great afternoon. Be a wonderful person in this world.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.